Namaste, welcome to Pythagoras Academy. This is VIKRAM DACHEPALY. In this video, I am going to talk about the concept of electric field. What is electric field in the first place? Electrostatic force is a non-contact force, meaning two charges need not touch each other in order to apply force on each other. We know that like charges repel from each other and unlike charges get attracted towards each other, and all this will happen without touching each other. And that concept is field. The force is operated via field. To define electric field, I can say it is the effect that any charge would create in its surrounding. The effect of the charge in the region in which it is placed is known as electric field. Now the question is, how do we measure that electric field? How do we measure the effect of the charge in a region in which it is placed? Because once we measure the electric field, then we can find the force experienced by another charge which comes into that field. So there are two physical quantities which are useful, which are defined to measure the strength of electric field in a region. Number one, it is electric field intensity vector. Number two, it is electric potential scalar. Just like in mechanics, we have velocity vector and speed scalar, two physical quantities which have their own definitions in order to describe how fast a particle is moving. Similarly, we have electric field intensity vector and electric potential scalar to measure the effect that a charge creates in its surrounding. Let us first talk about the electric field intensity vector. So electric field intensity vector is defined as the force experienced by a unit positive charge which is placed at that point. Suppose I bring a charge in a region, say this is charge Q, and it is creating its effect in the region, and that effect is not same everywhere. It varies from point to point. That is the reason why electric field intensity vector is defined at a particular point. Electric field intensity at a particular point. Now, if I choose point A here, somewhere in the region, and what is the effect of this charge at this point in terms of electric field intensity vector? So it is defined as the force experienced by a unit positive charge which is placed at that point. Meaning, I have to bring a 1 coulomb charge and place here at point A and see how much force this 1 coulomb charge is experiencing due to the electric field created by charge Q. So the force experienced by a unit positive charge plus 1 coulomb charge placed at that point. This is the definition of electric field. Now, because we know that 1 coulomb is really huge, if I really bring a 1 coulomb charge and place at A, in order to measure the electric field, 1 coulomb charge creates its own field in the region, and that might disturb the field caused by charge Q, because 1 coulomb charge is very, very huge. So my attempt to measure the effect of charge Q at point A will be failed. So that is the reason what we do is we bring a test charge. So in order to measure the electric field intensity at point A, I'll bring a test charge Q0 and place it at point A. Now what is test charge? Test charge is a very, very small positive charge. A small positive charge Q0. So Q0 is actually tending to 0. Smaller is the magnitude of the test charge, more accurate is my result. More accurate is the electric field that I am going to measure at point A, because it is not disturbing the already existing field created by charge Q. So bring a test charge, place it at point A. Now measure the force experienced by this test charge. Let it be F bar. It has got certain magnitude and direction. Now this is the force experienced by Q0 coulombs. As per the definition, I want to derive the force experienced by 1 coulomb. So I'll define I'll divide this force by Q naught. But this Q naught is very small, so limit Q naught is tending to 0. To get more accurate result, I have to choose Q naught, whose magnitude is infinitesimally small, as small as 0. It is tending to 0. So when Q naught is tending to 0, then even the force is also very small. So this is in the form of 0 by 0, a very small value divided by a very small value, which is a finite value. That is the electric field intensity vector at that point A. So this is the definition of electric field at a particular point A. Let us apply the same definition to derive the electric field created by a positive point charge Q at a distance r. So what we do is bring a test charge and the force experienced by it. So because Q is positive charge and Q naught is also positive charge, there is force of repulsion on Q naught, and that force is 1 by 4 pi epsilon naught capital Q's Q naught by r square by Coulomb's law. By definition, electric field at that point is limit Q naught tends to 0 F bar by Q naught. So if I have to define this force in terms of vectors, I'll write F bar and I'll multiply this with a unit vector r cap, where r cap is a unit vector in this direction. So solving this limit, when you divide this force by Q naught, we get a finite value, that is 1 by 4 pi epsilon naught Q by r square into r cap. The electric field intensity due to a point charge at a distance r from it is 1 by 4 pi epsilon naught Q by r square. It is in the direction away from the positive charge, and its magnitude is Q by 4 pi epsilon naught r square. And if you draw the graph of electric field versus distance, so it is decreasing with distance. As r tends to 0, electric field is infinity, and as r tends to infinity, electric field is tending to 0. So this is how we derive the electric field created by static charges. We can apply this result, we can extend this result to the electric field created by a ring of charge, a disk of charge, a linear charge, and so on. That's all. If you have any questions or suggestions, you can always use the comment section to interact with me. I'll be more than happy to help you out. This is Vikram DACHEPALY signing off. Namaste.